where you are at the moment. Thank you, Hans, for hosting this event. My name is Marcello Del Brenna, and I'm a representative of the High Voltage Systems Group of Europacable. Today I will talk about extra high voltage underground power cables, and in particular how we see them as a facilitator enabler for Europe's electricity supply. Taking into account the number of countries involved in this webinar, I will try to extend its reach beyond Europe as possible. But first of all, I would like to introduce Europacable to you. Many of you may not know who we are. Europacable is the Association of European Cable Manufacturers. Among the manufacturers who support and are members directly or indirectly of Europacable are companies who act in the domain of high voltage and extra high voltage cables, like the ones that you see in the slides, namely ABB, Brugg, Nexans, NKT, Prysmian, and Selec. Among the missions of Europacable, there is the harmonization of standards, and as far as high voltage systems is concerned, there is one working group, the High Voltage Systems Working Group, that deals mostly with cable systems for 220 kV and above. And this is the working group that I chair. Now, Europacable has many goals, and has many goals in many fields in the cable industry, both in the domain of energy and telecommunications. Among these goals, there is a contribution to the European standardization processes. There is the promotion of innovative technology, and in particular, and this is the subject of this webinar, for underground cable. And very important, we have to ensure as an association that there is a complete and correct understanding of what XLPE cable systems can and cannot do, and how they can contribute to the overall system. In particular, Europacable believes that extra high voltage XLPE cables are a modern, innovative, though reliable technology, with limited and in any case manageable environmental impact, and when compared to overheadlines, they present comparable life cycle costs. And in environments where it's more and more difficult to get overheadlines approved, if the cost of time lost due to permits problems and concerns from communes are considered as well, then the overall cost of a system can be comparable, if not lower. We are at the moment in a very special period in Europe, where on one side there is a very strong push from the European authorities and from the European community as a whole for the increase of a share of renewable energy into the grid. And at the same time, there is a big push to increase the efficiency of the grid in Europe, extending the grid beyond the national borders and creating a really integrated transmission network in Europe. What we believe is that underground cables can play a very important role in both fields, because they can facilitate grid extension by addressing the concerns of local communes. And not only that, they can also enable a quick and efficient integration of renewable energy. As you probably, most of you know, renewable energy is very frequently far away from where the load is, and besides the development of generation facilities for the renewables, it is important to take care as well of the investments and the extensions and the upgrades necessary to the network to support the transmission of this renewable energy to where the energy is actually needed. Now, we were talking about what are the pressures now, and so what are the energy priorities within the EU? The energy priorities within the EU are, on one side, the security of supply, of course, to ensure that energy flows electricity flows seamless across all countries in Europe. But among these priorities, there is certainly a key priority about climate change, and this means to increase the share of renewable energy, namely 20% by 2020, within the overall energy mix in Europe. On top of that, there is the need to ensure competitiveness in the electricity market, which means to unbundle, to separate generation, transmission and distribution, and to create an electricity market which grants access to all new competitors in the generation arena on one side, and allows the end user to buy the electricity in a free way, taking advantage of a competition which may be generated. What is the referee of this of a really functional electricity market is the transmission network. Only the transmission network can allow the end user to have a broad choice of supplier, and this is another one of the energy priorities. The consequences are very clear. There is a need of very significant infrastructure investment, both in terms of interconnection and in terms of new links to remote areas, in order to guarantee this link between generation and user. And the 10E programs, which were launched some years ago by the European Community, are gaining more and more momentum and more importance within this program. On the other side, there is the need for an increased coordination between the European Commission, the European Transmission Group, recently created, called ENTSO-E, and the regulators across Europe, in order to ensure that also not only the infrastructure ensures the goals of the European Union, but also that procedures, laws, regulations follow the same targets. It is also very important that the time span of the investment planning increases, and more reliable and more committal plans are built in a 10 to 15 years range, in order to ensure that the investments in the field of generation are followed or anticipated, if possible, by the investments and the upgrades necessary in the transmission network. This, of course, creates some sort of a rush and the need in many cases to create at local level some legislative tools that prevent to lose too much time in the execution of the projects, because if I want to ensure the targets by 2020, I need also to minimize the impact of bureaucracy, of permits, of discontent by the local population in the execution of the projects. Cost remains an important aspect in the execution of the project, but the fact of getting projects done becomes even more important. In that aspect, we can mention in Europe a couple of legislations which have been approved very recently, between the end of 2008 and the spring of 2009, in Germany and in Salzburg, where there is a first significant attempt to create rules to promote the partial undergrounding in the critical areas where one could expect the most discontent, protest and delays, and consequently delays in the execution of projects for the local stakeholders. populations, communes, associations, and so on. In both these legislations, there are some quantitative requirements, namely the distance from houses and the distance from residential areas, within which cables are either advised or have to be taken into consideration, or even in the case of Austria, they are required to be used. These are two legislations which are very recent, but which are being looked at in a very careful way also by other countries, trying to maximize the objectivity in the choice of the technologies to be used. Here again, what is being thought is not to replace overhead lines with cables, which would be totally useless and not feasible in practice, but create the right balance between cables and overhead lines, optimizing the cost, optimizing the performance, and most importantly, getting the projects approved in a timely manner in order to achieve the targets in terms of renewables and the free market as outlined before. Other projects are being discussed within Europe, and many more are being discussed also outside Europe. In Europe, we can mention the Bewley-Denny back transmission line in the northern part of the UK, in Scotland, where the main purpose is to bring south the electricity which will be produced by offshore wind farms in the North Sea. We mentioned the NLAC legislation in the slide before. Within the NLAC there are 4 pilot projects which are supposed to bring power from north to south, again to bring offshore power where the load is needed in the south. In Salzburg there is a very important project of the same nature, which is a key project to complete the ring, the extra high voltage ring, which will allow Austria to become a very important node within the import and export with neighboring countries, namely Italy, Switzerland, Slovakia and Germany. Similarly, a similar project is being discussed in Holland, where, to be fair, the tradition of underground cables is already well advanced and is a technology which has been in exclusive use up to 150 kV now for many years. Now, what are cable systems and what is the impact of cable systems in the environment, in the transmission network, and finally some discussion, a very short discussion on what are the costs, although this is probably the most difficult part to generalize. First of all, XLPE cables are an innovative, though reliable technology. As a matter of fact, up to 150 kV, there are at least 25 years of commercial experience, and in some countries even more than that. As I mentioned before, 150 kV nowadays in countries like Holland is almost is a technology, the only technology to be taken into consideration at this class of voltage. But if we go to the higher voltages, namely 220 and 400 kV, we have now more than 10 years experience of pieces of connections or parts of connections which are placed in very key locations in the transmission network. The longest system to date is a 40 kilometers link of 500 kV in Japan, which has been operating for more than 10 years now. So we can say without doubt that XLPE insulated cables are current state-of-the-art technology, and there has been and there continues to be work in order to make installation easier and pointing easier. The environmental risk is extremely low, and these systems have been designed in order to be maintenance free. The technical life expectancy for this cable is 40 years, but if we have to follow the experience at the lower voltage and the previous experience in the past generation cable systems, we can say that 40 years is probably a conservative time for what may be the real life of these systems. Regarding the cable lengths, normally these cables can be delivered in lengths of up to 1,000 meters, and the joint bays are generally unobstrusive underground structures to which access has to be granted in case of limited maintenance which may be needed from time to time, but which do not prevent the use of the land close and on top of it. Another myth which has been very often considered as a technical block are the overhead underground transition stations, which can be the size of a tennis court, maybe a little bit bigger, and this very much depends on what is the philosophy of the utilities and what sort of equipment they use in these transition stations. But at 275 kV and below, the transitions can be applied directly on pylons, and we have experience of that in France and other countries where the transition takes a very limited space. As far as damages are concerned, the experience accumulated not only at extra high voltage level but also at high voltage level show that underground cables can basically be damaged by outside influences. Being underground, they are not affected by weather, they are not affected by temperatures or winds or gales and so on, and which means that disturbances occur less often than for overhead lines. The cable quality is guaranteed by the testing standards which have been developed in the last years, and normally repairs caused by external damage mostly require, after the identification of the location of the fault, repair times of 2 to 3 weeks if spare parts are kept in stock. Now, the issue of the spare parts is something which has been recommended by the cable industry for a very long time, and for the key connections we appreciate that now it is the absolute norm. What has to be mentioned on top of that is that together with the development of the cable technology, together with the development of accessories technology, and together with the development of installation techniques technology, the research and development is making huge progress as well in diagnostic systems, which are able to monitor nowadays even online or offline the behavior of the components of a cable system, and can give very valuable information for the management of these cable systems, both in terms of maintenance or in terms of preventing overloads, or if when needed using these assets at their full potential. The result of that is that 400 kV projects have become more and more common during the years. In this slide you just see a short extract of what are the main projects in Europe, but nowadays we find XLPE cables at 400 kV in the Middle East. We find the projects in the Far East, in China at 500 kV. We find in North America at 345 kV as an example of a technology which has been picking up very quickly, especially from 2000 onwards, after the first flagship projects in Copenhagen and Berlin in the middle of the 90s, the second half of the 90s, which showed to the customers and to the public in general that the technology was viable and that it was feasible. From 2001 onwards, volumes have increased dramatically and continue to increase day after day. It is also fair to mention that besides high voltage AC technology, what is coming up, especially for interconnections, is HVDC technology. HVDC technology has been in use for many years, as far as cables are concerned, for submarine links with mass impregnated cables. We have many of these connections in Europe, and not only in Europe. The number of projects are growing very fast, and we can say that in the last 10 years there were more projects than in all the previous history of high power transmission. This is a technology which will continue to develop. It will continue to develop also in its XLPE form, and it's a cost-efficient alternative, especially for long connections point to point. They require converter stations to integrate it into AC grids, but there are circumstances in which it's a very interesting technology, and it's a technology which has to be considered as complementary to the traditional AC technology in what will be the development of a European and not only European grid. Let's talk now about some environmental issues. Of course, we cannot bluntly say that cable systems being underground do not impact the environment. Yes, they do impact the environment, but as you can see in the picture in the slide, they impact the environment in a very limited way, and more important, for a relatively short time. Indeed, even in extreme cases as the one showed in the picture with 4 cable systems, the total width of a corridor that will be occupied by the cable is quite limited and can be reinstated in a relatively short time. In general, 2 cable systems will carry a similar power to the one transmitted by one overhead line. And the number of the cables will depend on the overall power that will be needed. So there will be environmental impact during the execution of the works, but after the works are finished, experience made in many cases, and notably in the UK some years ago, show that after 18 to 24 months the landscape can be completely reinstated. This is extremely important because this allows, after a relatively limited period, to reutilize the land in the same way that it used to be before the installation of a new infrastructure. There have been discussions about the dangers of heating of the ground by underground cable systems due to the fact that cables run normally at temperatures around 80 to 90 degrees Celsius. In fact, the heat distribution around the cable depends on the backfill material which is selected to be put around the cable. But in any case, the impact is absolutely local and very limited, and with no impact for the wildlife and the vegetation which lives around the cable. The graph which has been developed by the University of Duisburg-Essen with experience with XLPE cables and with finite elements modeling, shows what are the temperatures around the cable, and basically there is no effect as soon as you are 4 to 5 meters outside the corridor occupied by the cables. This, what said before, basically means that after these 18-24 months, as a maximum, the land can come back to its original application. So it means that in the case of a city, of an area surrounding a city, normal life will start very quickly after the works are finished. But also in rural areas, land will be available for cultivation and for agricultural activities after some months after the works have been finished. And so there is no need for underground cables of the same right of ways and the same corridors which are normally needed for overhead lines. As far as electromagnetic fields are concerned, cables by their nature, being screened, they do not produce, they do not carry outside any electric field. They do create magnetic fields, but being underground, engineering solution can be found to reduce the level of magnetic fields as low as a few microtesla. Of course, the magnetic fields exist, but they can be managed down to the values which are deemed necessary depending on where the cables are installed. Being underground, they will not create any noise, any as overhead lines may do due to corona discharge and so on. So basically, cables will be invisible, silent, and with no impact whatsoever outside its corridor. The integration of cables in the transmission system. There is no basic problem to introduce XLPE cables in the transmission system. Yes, the cables have introduced capacity in the overall system. They are not inductive, they are capacitive, which may reduce the length, the maximum length which can be used depending on the voltage, and probably at 400 kV every 20-30 kilometers reactive compensation may be needed. But also in this case, reactive compensation is a very well-known technology with a limited cost and which doesn't require excessive space. It can be, on the contrary, beneficial to introduce into the network also some capacitive elements, provided that this is planned and this is calculated on the overall network from an overall network performance point of view. As far as transmission losses are concerned, using copper conductors and generally larger conductors than overhead lines, it is proved and demonstrated that cables have lower losses than overhead lines. This is one of the elements which bring the total life cycle cost of cable system much closer to overhead lines that the simple investment cost would suggest. As far as costs are concerned, we enter in this case in a very delicate area. By their nature, transmission projects are unique because all environments where cables or overhead lines can be installed differ one from each other, be it the type of soil, be it the type of geological place, be it the impact that it has on the local population, the local infrastructure. So to make generic cost estimates is extremely risky and doesn't bring any benefit for the parties involved. It is sure that underground cables are at installation more expensive than overhead lines. The product is more expensive simply due to the fact that we are talking about insulated conductors, screened and jacketed rather than bare conductors, and the installation cost will be higher since we have to dig holes, dig trenches, and install them underground. But if we start to consider other life cycle costs like maintenance, losses, unexpected outages, even the very brief outages which are present in overhead lines, then the picture will change. So what we can say is that overall the cost factors can reach 2 to 5 times if we consider the latest life cycle analysis calculations. An additional criteria has to be considered here, which is not very easy to calculate, but is a fact that it exists, which is the cost of not doing. In other words, what is the revenue stream that I lose due to delays in the approval processes? If this is taken into consideration, then is extremely likely that cable solutions, or better, mixed solution, cable and overhead lines, using the cables as facilitators in those areas where there is opposition, where permits are more difficult, then in this case partial undergrounding can prove to be also from a cost point of view a very attractive solution. Now, investment cost is one thing, total life cycle cost is another thing, cost of not doing is yet another thing. But it is also important to have an idea of what is the impact of of cabling, so of accepting an extra cost for cabling in infrastructure projects for the end user. Taking into account of the fact that transmission costs are a relatively limited part of the overall bill cost, and taking into account that the investment costs are spread on the consumer bills all across entire regions or entire countries, what we see is that the consequence of undergrounding on the bill of the end user is extremely limited. And this is a very important factor to take into account when analyzing the two processes. So this is just an example made in Lower Saxony in Germany, but partial cabling of a connection considered would increase the average domestic electricity price by 0.004 cents per kilowatt hour, which means 18 cents per year on the electricity bill, which is probably something that the end user would accept in exchange for a better landscape. Let's put it that way. Another question which is raised from every now and then, especially by utilities or by other parties interested in the transmission world, is with the increasing demand that we have in extra high voltage cables, what would be the impact of a further surge in demand for extra high voltage cables? Now, the European cable industry has been expanding production capacity. We have been expanding production capacity during the last years because we saw the trend growing, and we are in a situation today where we can, as a European cable manufacturer, to produce between 2,000 and 3,000 kilometers of cable, extra high voltage cable per year, which based on the present forecast should meet the demand in Europe up to 2015, which means on one side that the capacity it's a non-problem. On the other hand, if the growth trends were to be higher than the present trends that the industry is forecasting today, that all stakeholders are forecasting today, as other industries, also the cable industry would adapt and would put in the ground the capacity needed to satisfy the demands. So, what are the conclusions of this very short presentation? I mean, Europacable believes that XLPE cables are modern, innovative, and most importantly, reliable technology. It is a technology that impacts the environment, as all infrastructure investment do, but in a limited and, most importantly, in a very manageable way. On top of that, the total life cycle costs of the technology are comparable to overhead lines, especially if in combination with overhead lines. So we believe that partial undergrounding, that means undergrounding combined with overhead lines where there is no room to underground, can facilitate grid extension, so to accelerate the permitting process of projects and make available renewable energy sources and the competitive electricity to Europe's end user, and to allow Europe to meet the targets set for the energy mix of the future. Thank you very much.